Okay, good. So, hello everyone, we've met. So, this is a course on fluid dynamics, okay? And it's going to be divided into two parts. One is going to be what it used to be called fluid mechanics, okay? And so we will deal with the basic properties of fluids. We'll start with fluid statics. Well, we'll start with what is a fluid, and then we'll go into fluid statics, which is going to be very short, probably just today. And then we'll go into the fluid dynamics. Okay, so first describing the motion of fluids, and then describing the forces that are acting on fluids. So we'll describe all the different forces, and we'll go through a series of conservation laws. So I'll do those first 9 lectures that you see there. Okay, so we'll start with some basic introduction of what fluids are. Second lecture is going to be, just first part is going to be for most of you just reminding ourselves of things that we've seen before, which is okay. Okay, this should be a course. This should probably be the first course that you are given at the diploma, but for many reasons is not. Okay, also to allow PhD students to participate. So the beginning is going to be a lot of remembering things that we know roughly. Okay. So we'll use tensors a lot during this course. Okay, maybe not all of you are familiar with tensors, so we'll give some general introduction to what tensors are and how to define gradient, divergence, curl operators in tensor notation, in vector notation. Okay. Then we'll start talking about the kinematics of the flow. Okay, so just describing derivatives, streamlines, stream functions, and stream rates with tensors. So trying to understand the kinematics of fluids. We'll close the kinematics by the general relative motion near a point, which will give us a general description of the kinematics of the fluid. Okay. And we'll derive this very important vorticity and circulation theorem that you will use throughout the year. Okay? Very simple, most of you know them already, but we'll start deriving everything from first principles, okay? From what a Newtonian fluid is to the full momentum equations that you use every day in every course. Okay? So the beginning is going to be extremely simple, and then we'll go into the proper dynamics of the fluid. How can we describe the dynamics of the fluid? So we'll do conservation laws, mass or tracer, which you might use, if you're an atmospheric dynamicist, you might want to know how some tracer in the atmosphere is transported, for example, or in the ocean. Okay. The advection and diffusion equation, and then we'll go into the momentum equations. Okay, so we're going to derive the momentum equation for a fluid, and then we'll add the necessary forces for a geophysical fluid, okay, which is what we care about. We're not engineers. Well, you might be engineers, but you will become a GFD person, hopefully. And then we'll go to the conservation law for energy, okay, and so we'll do the energy equation and the Bernoulli equation, which is again very useful for geophysical fluid dynamicist. Okay. So these are going to be n-dynamic similarities, so a few useful numbers, non-dimensional numbers that we use every day in all our GFD. And then the second part of the course is going to be proper GFD, geophysical fluid dynamics. Okay? And that will be given by somebody else. So the course is divided into two, first 9 lectures and the second set of 9 lectures. Okay? And the second set of lectures is proper geophysical fluid dynamics. So you will use all the conservation laws that we have derived from first principles, and you will use those equations to describe GFD. Okay, so you might repeat some of the equations that we've seen: momentum and conservation, mass conservation, energy, and then you'll start deriving things like geostrophy, the effect, the importance of friction to generate some particular boundary layers. You'll look at waves, stratification, and mixing properties in GFD. Okay, so it doesn't matter if you're going to go for the atmosphere, the ocean, or even solid Earth. Those are all GFD fluids. Okay, so this is a very general course for. I guess this is an introductory course for all the courses that you will see: atmospheric dynamics, ocean dynamics that I will give in the second semester, and also all the courses in solid Earth, seismology, and everything else. Okay. So the beginning is going to be very simple and very basic. Just remember things that we know or we might not know, but it's going to be very simple. Okay. 18 lectures. First 9 given by me. Second set of 9 lectures given by somebody else. Only one exam, of course. One written exam. A few questions on the first part and a few questions on the second part. Okay. Any question, doubt, or things you want to go more in depth or whatever, send me an email, come and see me anytime. Okay. Don't wait the day before the exam. It's not a good idea in general. And that's it. You should know where we are. Okay, the ESP pool is not in this building, it's in the other building. Okay, so I tend to do most of the things on the blackboard. So for the other course, the Ocean Dynamics course, I have a nice set of notes, 150 pages of notes. Okay, because I have fun doing it. But for this course, I have a few slides that I show. Okay, for the first and second lectures, I'll show some slides. For the rest of the lectures, I'll probably not going to show any slide. Okay, so just things on the blackboard. So do take notes because there's not going to be any slides or notes provided. Okay, but it's very basic and everything. Whatever I say is in every introductory fluid mechanics book. Okay, I can give you the book that I use. The name of the book that I use is the standard Bachelor of Fluid Mechanics, or the Bachelor of Fluid Mechanics, the Kushmar-Razen GFD book. I think it's called Intro to GFD. Okay. Or Bachelor, Fluid Mechanics book, and well, then for the other course I use a different book. Okay, but any fluid mechanics or any fluid dynamics book will do for this basic first 9 lectures. Okay, doesn't matter which one you choose. It's just basic introductions to fluid mechanics. Okay, I can give you. So I'll whatever slide I have and notes that you might want. I'll create a Dropbox folder and I'll send you the link of the Dropbox folder, so you will find, for example, this syllabus. And I thought I had written down the name of the books, but I will. Okay, so I will add here books. Okay, and I will add the name of these books. Okay. So notes, I'm working on it, but not yet. Yeah, okay. So very basic definitions of fluids and everything else, okay? So why do we study fluids? Starting from very general reasons. Well, fluids are everywhere, okay? So it doesn't matter if you're an engineer working on pipes and hydraulics, if you're an environmental fluid dynamicist or fluid mechanics. The set of equations that we will develop and the conservation laws are valid for any kind of fluid that you might want to study. Okay? For example, I have colleagues working on exoplanets, okay, or all the different set of planets. For example, Jupiter, and they study the atmosphere of Jupiter, for example. Okay? And they use the same set of equations, GFD equations, that we are going to develop in this course. Okay? For example, that big red spot in Jupiter, okay, that can be described with the same set of equations that we'll be deriving during this course. Fluids are interesting to study because they have many properties, and we'll see some of them, okay, not all of them. But even if there's a group here, ICTP, working on quantitative life sciences, so it's the interaction between physics and biology. And they're also fluid dynamicists. They use a lot of turbulence, they use a lot of GFD, well, maybe not GFD, but they use a lot of fluid dynamics, okay? And they study the behavior of certain animals, for example, okay? And they use the similar set of equations that we're going to develop here, okay? So if you're a physicist interested in biological problems, you use the same set of equations, the same properties of fluid. For example, how an animal can walk or stay on a liquid film, for example, okay? Fluids can have many different properties. We'll see these particular properties of fluids today. But also fluids, you know, they can be laminar or they can be turbulent. Laminar fluids are very different to turbulent fluids. Most of the fluids are turbulent. We're not going to go into turbulence in this course. Okay, there's a separate course on turbulence for PhD students, and turbulence will be there will be an introduction to turbulence in a different course in the second semester. It's called climate modeling. Okay. So there will be a little introduction on turbulence and how to make parameterizations for turbulent properties that are not resolved in climate models. Okay. We're interested in fluids because fluids, as we will see today, fluids change. The fluids change with time, and fluids change depending on the environment. So the properties are dependent on time, and they are dependent on the environment where they are. Okay. For example, you could be a fluid dynamicist and working on rivers for whatever reason you want. Okay. And in this picture, you see that the same fluid has two different behaviors. On one side of the river is a quasi-laminar fluid, and in a different region it is a very turbulent fluid. Okay, so same fluid, but depending on the environment, it could be laminar or it could be turbulent, for example. So if you're interested in, for example, sediment dynamics, you might want to know when the fluid is laminar, when the fluid is turbulent, how it changes with time, and so on and so forth. Okay. Funny examples of turbulent fluids. If you're not a scientist, but you just want to go down a river with a canoe or a kayak, okay, that person doesn't know, might not know, maybe does, a lot of GFD, maybe he doesn't know a lot of GFD, but he knows that if he wants to have a rest when he's going down the river, he should go downstream of that big rock. Because downstream of that big rock, the fluid behaves like this. This is a simulation, a computer simulation of a fluid, okay? And this this black circle is, for example, a rock, okay? And so the fluid is flowing from left to right, starts as a laminar fluid. You see all these streamlines that we will describe in detail. All these white streamlines that are describing the flow, okay? They don't tell you why the flow is going the way it is going, but they describe the flow. So this flow is laminar, so all these streamlines they all have the same property in space, and then after hitting the object, you see that there are some strange patterns arising. And all those strange patterns means that the fluid is becoming turbulent, and there are certain things happening past the object. And you see that right on the wake of the object, there are no streamlines. That means that the flow there has almost zero velocity, okay? For reasons that you will see in the second part of the course, where you will study instabilities of the fluid, okay? So if you want to have a rest going down the canoe, you want to put yourself here where the fluid is almost with zero velocity, okay? This is another interesting and curious pattern of geophysical fluids that in certain conditions you might form these are called Taylor-Proudman curtains. Okay? So imagine you have an obstacle, which is this green thing, and if you have a fluid going again from left to right, that fluid under certain conditions is constrained to have the same properties with depth or with height. Okay? So usually when I talk, so I'm an oceanographer, so I'm a physical oceanographer. So I think of GFD as an oceanographer. So every time there is a choice between height and depth, I say depth. And every time there is a choice between atmosphere and ocean, I say ocean. But if I say ocean, it's valid also for the atmosphere, of course. Okay? So, and if I give example, it's usually an oceanographic example. But that doesn't mean that whatever I say only applies to the ocean. So under certain conditions, the fluid is constrained to have the same property at each depth. Okay? And so if there is an obstacle, for example, a rock, that doesn't go all the way to the surface, this fluid, when it encounters the obstacle or the rock, is forced to go around the object, okay, under certain conditions. And because the fluid is constrained to have the same properties with depth, all the fluid particles that are above the obstacles are also doing whatever the fluid is doing down at the bottom. So all these fluid particles are also going around the object, even though the object is not there anymore. Okay? That's a theoretical result called Taylor-Proudman curtains, but is also observed in some special conditions. Okay? So in this particular fluid, everything in depth is constant. So if the flow has to go around the rock at a certain depth, all the fluid at all depths will have to go the same direction. Okay? And so you can study those problems, which again are valid for the ocean, for the atmosphere, or any geophysical fluid, through the equations that we will develop in this course. Okay? So a few examples of all the fluid properties that we will study in this part of the course, but also in the second part of the course. Atmospheric phenomena, tornadoes, for example. We've had here in Italy recently a lot of rain. I don't know if you've read the news, or seen the news. Okay, lots of interesting but damaging atmospheric conditions, and those can be explained by GFD equations. Okay. Some funny condensation clouds over a mountain. Okay, all those can be explained through thermodynamics and GFD. Another instability that you will see in the second part of the course is this one called Kelvin-Helmholtz instability. Okay, these are two different fluids with two different densities. One is blue and one is red. Red, I believe, is denser. Okay, and if you develop an instability in this two-layer fluids, on the interface there will be a wave developing, okay, and eventually the blue and the red will mix because this wave will break through an instability process, okay, and so eventually there will be a mix between blue and red at the interface. Okay, this is again a numerical simulation, very nice and clean, of this instability problem, GFD instability problem, but you can actually observe this Kelvin-Helmholtz instability. These are clouds, okay? So you have a very stable boundary layer over the ocean, very warm air, and you have cold air at the top, and then for some reason you start an instability, and there are these nice waves developing at the interface, and you can see this interface in these waves because there are clouds at that interface. So, theory works. Oceanographic phenomena, of course. Okay, very similar examples, but slightly different. This is a satellite picture of, I think, somewhere close to the Arctic Ocean. And what you see in green or bright colors is sea ice. and the blue, the dark blue, is the seawater. So what you see here is nice circular patterns and filaments, okay, that are deformed, and those structures are formed because of properties of the fluid, of the oceanic fluid. Okay, the size of these structures are determined by a certain no-dimensional number that you will see in the second part of the course. Another example is the surface circulation of the ocean. Okay, white is surface speed. So you see all this white current here. This is called the Gulf Stream. Maybe some of you have heard of it. Okay, very fast current on the western side of the Atlantic Ocean, and all those circular patterns are due again to instabilities in the ocean, and the size of those circular patterns are determined by the latitude and the structure and the stratification of the ocean. These are roughly the equivalent to the cyclones and anticyclones in the atmosphere. Okay? In the ocean you also have cyclones and anticyclones. They're much smaller mostly because of stratification, and they have similar importance to the ocean as in the atmosphere. This is a satellite image of the Gulf Stream. You see this red, now this is temperature, surface temperature, red is warm, and blue and green is colder. Okay? So you see this red and warm current flowing towards the north, and then it starts mixing and forming, you see these circular patterns here. So those circular patterns are again instabilities of the flow, and those instability will bring you to mixing of the tracer in the ocean, same thing in the atmosphere. And those are extremely important for mixing properties, for mixing waters or fluids of different characteristics, and they will affect both locally but also the large-scale circulation. Okay? Same thing as in the atmosphere. In the ocean usually everything is much smaller because of the different properties of the oceanic fluid. If you're not interested in climate, the atmosphere, and the ocean, GFD applies to the solid Earth as well. This is lava. Okay, you can study the interior of the Earth where there's fluids. They have different viscosities, different temperatures, whatever you like, but the fluid obeys the same laws of conservation laws and the same energy, conservation of energy. Okay. So whatever you're interested in, you need to know what is a fluid, okay, and how fluid moves and why fluid is moving the way it is moving. Okay. So again, very basic introduction to fluid. What is a fluid? Fluid is not just water or air fluid or water. Could be water if you're more interested in the ocean or rivers or things like that. Could be the air if you're interested in the atmospheric side of the fluid dynamics, or it could be oil, any kind of oil that you're interested in if you're more applied to the engineering side, for example. Okay. What is a fluid versus no fluid? Sometimes the distinction between a fluid and what is not a fluid is not so clear. So basic intuitive definitions of fluid, they flow, okay, easy, but we'll see what does that mean that the fluid flows in terms of equations. Fluid deforms depending on the environment, okay, a river, an ocean, an atmosphere, lava in the interior of the ocean, and it takes the form of the container, of course. Okay, so this could be all the reasons why you want to study fluid mechanics. We are just interested in the red part of it. Okay, meteorology, oceanography, geophysics, sediment dynamics, if you like. Okay, but also if you're more interested in the health applications of fluid, there are people doing PhD here with us looking at fluid dynamics of blood in terms of heart diseases, for example. Or if you're coming from an engineering side, you might have a background in aerodynamics or things like that. So where does fluid mechanics stands in the continues of mechanics? Well, this is a simple diagram telling you where we are. Okay, fluid mechanics is somewhere here, And we can divide the fluid dynamics into statics and dynamics. Statics we're basically doing today and maybe a little bit tomorrow, but not so interesting for us. But fluid dynamics is really what is interesting to us. Okay. Then we're going to go into boundary problems, especially in the second part. Okay, so the formation of boundary layers in fluids. Those apply to the ocean, they apply to the atmosphere. Boundary layers are extremely important if you're thinking about the ocean, how, for example, the wind is blowing over the ocean and is causing dynamics. Okay, boundary layer there at the surface of the ocean is very important. You need to understand how that works. Boundary layer in the atmosphere is also very important. Okay. Internal flow, and all these flows can be laminar or turbulent. Most of the fluid and the flows that we are going to study are going to be turbulent because that's the reality. Okay, so we're going to cover this first three: statics, very simple; kinematics, describing the velocities and describing the motion of the fluid through streamlines, velocity near a point, stream functions, and so on. And then the proper dynamics of the fluid, so studying the velocity and the accelerations and all the forces acting on the fluid and given the characteristics to the fluid. And then the second part will get you into the proper GFD, the application of all this to GFD. Okay, so some basic properties of fluids, definitions, dimensions, mass, and so on. So the definition of a fluid, a little bit more or less intuitive than it flows. So what is a fluid? A fluid is a substance that deforms continuously when acted on by a shearing stress. Okay, so there is a stress on a fluid and the fluid starts to deform. And it deforms continuously as long as there is a shear stress acting on the fluid. Okay. What is a shear stress? Shear stress is a tangential force, so it's not a normal force, but it's a tangential force per unit area. It's a simple diagram. You have the area, blue area. There's a force tangential to the area that will give you a shear stress acting on the fluid. And the fluid will deform continuously as long as there is a force, shear stress acting on the fluid. Okay? That's very different from a solid. In a solid, you apply a force to a solid and the solid will deform, but it doesn't deform continuously. It deforms, it takes a new shape, but it doesn't deform continuously. Different examples of shear stresses if you are on the solid earth side. A fault, okay, is an example of a shear stress between two sides of the fault. You have many stresses. It can be compressional, it can be tensional, or it can be a shear stress, which is what we care about in a fluid. Okay. So if this is the area A, you can have two stresses acting on it. One is a normal stress, okay, in the normal direction to the area, and the other one is the shear component of this force acting on the area of the fluid. Okay. So it's not a fluid. Examples: rubber, ice, and steel. These are solid, so they can deform to a new equilibrium after you apply a force. Okay. So when shear stress is applied, they can deform to a new equilibrium. They don't have to, but they can, depending on the rigidity. But they don't flow like a liquid because of structural rigidity. Okay, so they change their shape into a new equilibrium, but they're not deforming continuously. They might break, they might get to a new state, but they don't deform continuously. And that's because of structural rigidity. Substance like shape of container, fluid versus not fluid. Fluid, for example, a liquid water, deforms assuming the shape of a glass when you fill the glass, okay? And gravity provides the force. Then we'll talk about statics today. So when the balance is achieved between the force by the walls and the force exerted by gravity, then the fluid is in static condition, okay? The fluid in that glass of water doesn't move, therefore that fluid is in static condition. And static means there is a balance between forces, not that there are no forces, just there is a balance between different forces. In this case, it's the forces exerted by the walls of the glass and gravity on the fluid. Okay? when you pour ice cubes in the glass, the ice cubes fall into the glass, but they don't deform continuously and take the shape of the glass, okay? So those solid ice cubes, they maintain the original shape and they don't deform, okay? So that's another intuitive difference between a solid and a liquid. So distinction between solid and fluid. Why are they so different? Because in a solid the molecules are much closer together than in a fluid. That's structural rigidity. There can be different solids. For example, an elastic solid, they deform under a load. Okay, this is not going to deform, but there are some solids that deform under a load, and then they might recover the original state when you take away the force. Okay, good example could be, some solid that they deform when you apply a force. When you remove the force, they go back to the original shape. That's an elastic solid. Okay, a plastic solid deforms under the load and does not return to the original state. So it changes and it goes into a new equilibrium state. Okay, after you apply the force, but they're still solid. They don't deform continuously when acted on by a shear stress. Okay, they break into a new state, but not continuously. Fluids is not just liquids; it's also gases, of course. Okay, so fluids can be gas and liquid. What is the difference? In a gas, molecules are much further apart. They're very compressible. Gases are very compressible, and they tend to expand indefinitely. Okay, a gas in this room expands indefinitely until it fills the whole volume. A liquid is relatively incompressible. It is incompressible, but very often, both in atmospheric dynamics and in ocean dynamics, we'll make the assumption of incompressibility, even though those fluids are compressible, but not very compressible. And it does not expand so much with pressure. Okay, it does a little bit. That's why it matters, but not so much as a gas. Does it matter? Dimensions and unit. Very boring. Qualitative description of a fluid, dimensions, length and time and velocity, or you might describe it quantitatively, a number plus a unit, gravity 9.8 meters per second. What are the dimensions? There are primary dimensions and derived dimensions. Examples of primary dimensions: mass, length, time, force, length and time again. Derived dimensions, for example, velocity. Okay, velocity is derived from length and time. Okay. This is all ways of describing fluids. Units that you use, all GFDs and so on and so forth: meters, kilograms, Newton. Okay, for forces. Temperatures, both in Kelvin and in Celsius. It doesn't matter. Okay. Mass and weights. Weight is mass times gravitational acceleration. So the weight, for example, of 1 kilogram of mass is 9.81 Newton. Okay. For the same mass, you can have different weights. Okay, that's pretty obvious. For example, you go to the moon, your weight is not the same as the weight that you have here on Earth, because gravity is much smaller than here. Okay, properties of fluids, for example, density. You'll talk about density all year, okay, because it's one of the basic properties of the fluid, especially when you're trying to describe the dynamics of the fluid in the atmosphere and the ocean. We talk a lot about density because density will make the fluid move. Okay, there are density currents in the ocean, there are density currents in the atmosphere, okay, and in the interior of the Earth. So density is something that you will be talking about a lot. And density varies, obviously, from one fluid to the other, but also density varies with temperature, with pressure, so for example with height. Okay, one thing that, for example, in the atmosphere, you look a lot at, for example, the sea level pressure. Okay, sea level pressure. This is a map of sea level pressure observations. So at sea level, what is the pressure? You have a lot of pressure here, you have a height with an H, and you have a low here below, okay? And that will determine the circulation in the atmosphere, and the same thing applies to the ocean, okay? You have different pressures, you will start developing pressure gradients, and pressure gradients will start move your fluid, could be the atmosphere or the ocean, okay? So density affects movements, and density is a function of pressure, for example. Okay, density of common fluids, water 1,000 kilograms per meter cube. Seawater is denser because we have salts. Okay, we'll talk about that a lot in the ocean dynamics course. Crude oil is less dense than seawater, that's why it floats on top of water. Air is much lighter than water, of course. So fluids is not only liquid, it's also gases. Okay, for example, perfect gases, I guess you've seen all of this in the Thermodynamics course. Gases with constant specific heats, that obey the perfect gas law, is P over rho RT. And the specific heat is the amount of heat per unit mass required to raise the temperature by 1 degree Celsius. Okay, so that C could be a CP depending on how you want to write it. Okay? So that's the specific heat of a fluid particle. So describing the fluids, we're going to do a lot of approximations when we describe the fluid, and we're going to do a lot of approximations when we describe the dynamics of fluids. Okay, just to make things simpler, or because we're interested in one particular characteristic of the fluid. Okay, we don't want to know what is happening to the fluid near the boundaries. We don't want to know what is happening to the fluid in time. Okay, and so when we will have all our equations of motion, for example, we'll say, okay, well, in this particular situation or for this particular problem, this term or this force or this property of the fluid is what really matters for this dynamics, or is what I'm really interested in. Okay, so we'll make approximations by saying this term or this force is much more important than the other, so I neglect this other term in the equation or this other force. Okay, that doesn't mean that that term or that force is equal to zero. We're just saying that this is larger than this, or this is bigger than that, and so we just consider the effect of this big force on this very, very small force. So we approximate the equations of motion, for example, okay, to study the particular behavior of one fluid in one place or under certain conditions. Okay. For example, somebody makes use of ideal fluids to describe the fluid properties or particular behavior of fluids. Okay, so what is an ideal fluid? If you remember that image of an obstacle, the black circular obstacle, and then all the streamlines going through the obstacle. In the first image, we had some circle, red, black obstacle like this. We have the streamlines going like this, okay, in a laminar way, and then things were happening here. Okay? Things were becoming turbulent. And so the behavior of the fluid past the obstacle was much different than the behavior of the fluid before the obstacle. And that's because of a lot of friction interaction with the obstacle and so on. One of the simplifications, very big simplifications you can do, is to study ideal fluids. Okay? An ideal fluid is a fluid with no friction. Okay? In a fluid with no friction, if you don't have any friction, and if you don't have any viscosity, then the fluid characteristics are the same at all times. They're not affected by the obstacle, or they're not affected by the boundaries where the fluid is flowing. Okay? So that's why you see in that top right corner image that the fluid characteristics after the obstacle and before the obstacle are the same, as opposed to the previous case. Okay. So an ideal fluid is a fluid with no friction, and is also said to be an inviscid fluid. Okay. Inviscid meaning no viscosity. All the internal forces at any section are normal. So if you make a section here, all the forces acting on this fluid are normal to the fluid. meaning that there are no shear forces. If there were shear forces, there would be friction, viscosity, friction arising from the shear stress. So there are no shear stresses, there's only normal forces, and we'll see that the only normal force acting on the fluid can be pressure. Okay? You might think, ideal fluid are only imaginary fluids, okay? Ideal fluids don't exist, that's why they're called ideal. Because every fluid has some kind of viscosity. Every fluid has some kind of viscosity, and every fluid has some kind of friction with another fluid or a solid boundary. Okay? So it's a simplification, it's an imaginary fluid, but it's quite interesting to study ideal fluids in some conditions because, as I said before, you might not be interested in describing all the properties of the fluid. Sometimes you're interested in some particular properties of the fluid. For example, you're not interested in the dynamics close to the boundaries. Okay, so many flows can be considered frictionless, with no friction, as long as they are away from solid boundaries. Okay, so if you're thinking of the ocean, I am thinking of the ocean. Okay, and if this is your ocean, an idealized thinking of the ocean. Okay, here at the surface you have some wind blowing on the surface of the ocean. Here you have continents. Okay, here you have continents as well. Here you have bathymetry at the bottom of the ocean. Okay, so you have friction. You have friction here. You have friction here. You have friction close to the bottom of the ocean. You have friction at the surface of the ocean. Okay, but if you're studying what is happening here in the interior of the ocean, you might consider the flow to be frictionless. Okay, so if you are interested in the dynamics of the upper ocean, for example, and you want to know how the wind is affecting the surface of the ocean, then you cannot consider an ideal fluid or a frictionless fluid, because friction is going to be very important here, friction with the shear stress given by the wind, and that will determine the dynamics of the ocean or the dynamics of the atmosphere. If you're studying dynamics close to the bottom of the ocean or close to the mountains in the atmosphere, you need friction as well, and the same thing at the boundaries. Okay. But if you're looking at if you're thinking about the large-scale ocean circulation or the large-scale atmospheric circulation, you might consider the fluid to be frictionless, away from the boundaries, and just studying what is happening in the interior of the fluid. Okay? In the interior of the fluid, which could be the atmosphere of the ocean. And then you say, okay, so if I don't consider friction, what are the forces acting on this fluid, and what is the force balance in this interior of the ocean or interior of the atmosphere? And you end up with some particular theories, for example, just trophic balance in the atmosphere or just trophic balance in the ocean, where you don't consider friction, but you only consider pressure gradients and the rotation of the Earth, for example. Okay? So in that case, you make the approximation of no friction, but that doesn't mean that the fluid doesn't have any friction. You're just studying one particular aspect of the fluid, which is the interior of the fluid. Okay? So even though ideal fluids do not exist, it is useful sometimes to consider the fluid to be frictionless, because that helps you reduce the problem to a simpler set of equations, where you can really see what is the effect of the main forces acting on the fluid. Okay. Real fluids, which is what we care about, they do have friction. Okay. And so when you have tangential or shearing forces, they develop every time you have friction. Okay? So in a real fluid, you create friction when you have shear forces. Remember, in an ideal fluid, you cannot have shear forces, you only have normal forces. So if you have shear forces or shear stresses, which are tangential to the area, then you create friction, which is trying to oppose the movement of the fluid. Okay? And friction gives rise to a fluid property which is called the viscosity, which is very important for every kind of fluid that you study. Okay, so now we're going to look at what the viscosity is, definition of viscosity, how you can relate the shear stress on the fluid to the viscosity, and derive the Newton's law of viscosity, which is quite simple, and look at different values of viscosities for different fluids. Okay, so what is the viscosity? Viscosity is a measure of the resistance of the fluid to being deformed. So remember, a fluid deforms continuously when acted on by a shear stress, not like a solid. And so when you have a force and it's a shear stress, it's trying to deform continuously the fluid, but not every fluid deforms in the same way. And the difference in deforming is given by the viscosity. When the fluid has low viscosity, they're called thin fluids, okay? And so they can be easily deformed. So a little bit of shear stress and you can deform the fluid. When the fluids have high viscosity, they're called thick, and they need a lot of shear stress to be deformed. Those are two examples of thick fluids, okay? Chocolate and milk. Those have a lot of viscosity, and it takes much more shear stress to deform those fluids as opposed to water, for example. This example doesn't work, so we'll see a different one. Okay, so now we're going to derive the viscosity and the Newton's law of viscosity. Okay, so imagine you have two plates, and in the middle of the two plates there is a fluid. We have a depth or height h. We have a force acting on this plate. Okay, this is three-dimensional. We have a force acting on this plate, and the shear stress is proportional to the force per unit area, and this is my area A. Okay, so that's my shear stress. So when I apply this force or this shear stress on the top plate of the fluid, then the fluid starts moving and deforming continuously because it's a fluid. Okay, and so at the beginning the top plate used to be here on top of the bottom plate, and after a certain time it has been deformed in that direction by this shear stress, okay, with some delta L, and we have formed an angle delta beta. Okay? So coordinates could be three-dimensional, doesn't matter. So we have a velocity of the fluid, whereby the velocity of the fluid here is u naught, whatever that is, given by the shear stress at the surface, and the bottom plate is fixed so that u at the bottom is equal to 0. Okay, and so the velocity within the fluid is a function of depth. Okay, and to make things simpler, is a linear function of depth. So velocity varies linearly from u naught to 0, so that you can write the velocity as u naught z h. Okay, so that when h at the top, u is u naught, and when z is equal to 0, then u is equal to 0. Okay? So that's a linear variation of the velocity with depth. So now that we have that if the shear stress F over A increases, if this increases, then your u naught increases. Okay, so the velocity is a function of the shear stress, of course. So the stronger the force, the faster the fluid deforms under the shear stress. And if the depth increases, u naught also increases. Yes. Okay, because you are away from the bottom panel that is fixed. Okay, so you start thinking already of friction. So the thicker the fluid, the faster the u naught at the surface, because you are away from the bottom panel. Okay, so this means that your u naught is proportional to F over A and to H. Okay? The larger the shear stress, the larger the u naught. The larger H, the larger your u naught. So this means that u naught over H, is proportional to F over A, which is your shear stress. Okay, so your u naught over H is proportional to the shear stress. Now we can define our shear stress, and we're going to start using annotation. So the shear stress acting on the x, z plane, which is equal to F over A, my force per unit area. This, we said, is proportional to u naught over H. Okay, so we can say already that my shear stress, z, is going to be equal to some mu times u naught over H. Okay, where this Greek letter mu is going to be my constant of proportionality between my shear stress and my u naught over H, which is going to be the way u varies with H. Okay, so that's intuitively this is how a force acting on a fluid is causing a shear stress, and the shear stress is deforming the fluid continuously in a simple approximation linearly. And so this is how you can relate the shear stress to the movement of the fluid through some constant that we will see what that constant is. Now let's try to go a little bit deeper into this. So after some time delta t, the fluid has deformed by this delta L, right? So this top plate used to be here. There's a shear stress which moves the plate, and after some time delta t, the top plate has been deformed and moved some delta L. So after some delta t, you have delta L equal to u delta t. Okay, that's the space that the fluid has been deformed, which is this. This is delta B. This is delta L. Okay. Now, if delta t is sufficiently small, so if delta t is very small, you can approximate the tangent of delta B to delta B, some trigonometry. Okay, so that which is equal to delta L over H. This is H. Okay, this is just this. Okay. So for very small delta t, tangent of delta b is equal to delta b. So you can approximate that to delta b, and delta b is delta L over H. So that delta b is delta L u delta t over H. Okay, so delta b over delta t is u over H. So delta b, which is the deformation of the fluid, is a function of time, of course. Okay, that's because a fluid deforms continuously when there is a shear stress applied to the fluid. The shear stress is applied to the fluid, and delta b increases with time. So delta b is a function of time. And this is opposite to solids. When you apply a shear stress on a solid, you might create a delta b because the solid deforms to a new equilibrium state, but delta b doesn't change with time. Okay? You apply a stress to a solid, the solid deforms, and it stays where it is. So delta b is not a function of time. In a fluid, as long as you apply a shear stress, the fluid will continue to deform. So delta b is a function of time. So we're not so much interested in delta b, but we're interested in the rate of change of delta b. Okay? And it's something that you will do all year round when you study fluid. You're not interested in the velocity of the fluid or the energy of the fluid or whatever of the fluid. Most of the time you're interested in the rate of change of the fluid or the properties of the fluid. Okay? There's going to be d by dt everywhere in your equations. Okay? So you're interested in the rate of change. Okay? So if we're interested in the rate of change, we're interested in the rate of shearing strain. Okay, delta B is the strain, the shearing strain of the liquid, or the fluid, sorry. So this is what we care about, the rate of shearing strain, not just the shearing strain per se, as in a solid, but we're interested in a rate of change. Questions? No? And so if we're interested in the rate of change of the shear strain, again remember for very small delta t, then we can define the rate of change of the shear strain in the limit of delta t going to 0 of this delta b times delta t. Okay? You'll see this is all very simple. So this is the rate of change that we're interested in. Okay? To the limit as delta t is very small and goes to 0. Now remember we have a linear profile of u with depth, which was this. Okay? And so we have a velocity gradient, which is going to be du by dz in this fluid. Okay? U varies with depth or height in a certain way, du by dz. And so we have a velocity gradient there. And in this case, because it's linear, the velocity gradient is a constant. Okay? It's just a simplification, it doesn't have to be. So, because it's a constant, we have that du by dz, which is a constant in this case, is equal to u naught over h. Okay? Du by dz is equal to u naught over h, because it's a constant in this linear case. And now we can substitute this into the rate of change of my shearing strain, my delta b. Okay, so now I can go here and say my, what was it? This, remember this? Okay. this is mu naught over h, okay? Putting this here. And u naught over h is du by dz. So, and this is proportional, and this we said is proportional to the shear stress, okay? So as the shear stress increases, my velocity gradient du by dz increases, and so it does my rate of change of my shear strain. So now I can write that okay, I've just related my, now what I've done is related my shear stress to the velocity gradient, which is really what I'm interested in. Okay, bless you. So we have a linear dependency of the velocity within the fluid, okay, which is like this. So my du by dz, the dependency of the velocity on the vertical is du by dz equal u naught over h, okay, and u naught over h is proportional to my shear stress. Now what I'm interested in is the rate of change of my shear strain or the deformation, okay. So the deformation is delta b in time, okay, how this angle delta b increases or decreases in time, and that is given by u over h. But u over h is simply the velocity gradient, okay. So the rate of change of my shear strain, so the deformation, is du by dz. So my shear stress, how do I relate my shear stress, or the force that I'm applying to the fluid, to the velocity gradient, is through this constant of proportionality called mu. Okay? So what it says is that I have a fluid, I have a shear stress at the surface, and the fluid will deform, and the velocity of the fluid inside of the fluid will depend on the vertical, in this case linearly, and it will have a velocity gradient, okay? The velocity gradient might be larger or it might be smaller, depending on the shear stress, okay? Strong shear stress, strong velocity gradient. So this is how you relate the shear stress to the velocity gradient of the fluid. The fluid starts to form continuously as long as you have a shear stress. And you generate a velocity gradient. Without a shear stress, velocity gradient is equal to zero, velocity is equal to zero. As soon as you apply a shear stress, you create a velocity gradient because you deform the fluid. The velocity at the surface will go like u naught, and the velocity at the bottom will be zero. You will have a strong velocity gradient for a strong shear stress, okay? But it also depends on the fluid, because you might have the same shear stress on the same fluid, and you will develop a different velocity gradient. And that's because every fluid has a different mu. Okay? So in water, you have a shear stress, the water deforms very easily, and you have a strong velocity gradient. If you use the same shear stress on honey, okay, you will deform honey not as much as water, and you will create a velocity gradient, for example, like this, and not like this. So the velocity gradient will be smaller with the same shear stress, and that's because this constant of proportionality has changed. Okay? And this is what we call viscosity. Okay? That's the viscosity of the fluid. So the more viscous the fluid, the smaller the velocity gradient that you create. And the less viscous the fluid, the larger the velocity gradient that you create. And so the viscosity is the resistance of the fluid to being deformed by a shear stress. Okay, so this is the okay, and this is called the Newton's law of viscosity. Okay, very simple. So, and what the Newton's law of viscosity is doing is relating the shear stress to the velocity gradient within the fluid. So the shear stress is going to be equal to the velocity gradient times some viscosity. And in a Newtonian fluid, that viscosity is a constant, is a value. Okay? So now we can define two different kinds of fluids. One fluid that is called Newtonian, which is what we talk about every day, and different fluids that are called non-Newtonian, okay? Which in environmental environments, in environmental problems, we don't care so much. Okay? So what is a Newtonian fluid? A Newtonian fluid obeys Newtonian law of viscosity, of course. And so the velocity gradient, which we also call the shear rate or the shear strain, is that there should be du by dz, okay? And there is a slope which is given by the viscosity, okay? So you can plot your shear stress on the y-axis, your shear rate, or du by dz, your velocity gradient, and then the slope of that line is going to be your viscosity. And the different slopes, different viscosity for different fluids. Okay. Units of viscosity is probably not the if you've dealt with viscosity before. So units of viscosity are Newton meter square by meter per second. This is the -1, which is equal to Newton seconds meter to the -2. But you could actually talk about, I don't remember if I've done this, you can actually talk about kinematic viscosity. Okay? So this is mu. You can talk about kinematic viscosity, which is your viscosity divided by density. Okay? This is something that we use a lot in the equation of motions. Okay? The kinematic viscosity, which is mu over rho, which gives you a much simpler unit, which is meter square per second. Okay? You go from this unit divided by rho, kilogram per meter cube, and you get meter square per second. So when you're not in an ideal fluid, but you are in a real fluid and you have viscosity, like in every case, okay? For example, if you're studying the upper ocean and you're studying the effect of the wind stress on the ocean, you will have some forces acting on your fluid, so you will have some acceleration terms equal to all the forces, your wind stress, for example in the x direction, and a kinematic viscosity parameter nu. Okay? Usually you don't find mu, unless you had rho times something and your mu, and usually you bring this down here to get the kinematic viscosity. Okay? So usually we work in kinematic viscosity. Okay, so this is the Newton's law of viscosity relating the shear stress to the velocity gradient. And again, while we're interested, oceanographic example, wind stress blowing over the surface of the ocean, pushing the ocean in one direction, creating a velocity gradient at the surface of the ocean. Okay, for example, this is the surface of the ocean, wind is blowing in one direction, pushing the ocean in one direction, creating a velocity gradient. And that velocity gradient is related to the wind, my shear stress, through a viscosity parameter. Okay? And that parameter depends on many things. Okay, so this is a Newtonian fluid, which is what we usually deal with. But of course, if there's a Newtonian fluid, there's something that is no Newtonian fluid. Okay? That's Newton, of course. So a no Newtonian fluid, and there are many no Newtonian fluids that you might have not realized before. So examples of no Newtonian fluid: you have paint, blood, cornstarch, water cornstarch, no cornstarch. Okay. If you're good at cooking, you use cornstarch all the time. Okay, and what is a non-Newtonian fluid? A non-Newtonian fluid is a fluid where viscosity depends on the shear rate. So in a Newtonian fluid, my viscosity is a constant. Okay? That's a Newtonian fluid. For a given pressure, temperature, whatever, water has a certain viscosity. For a non-Newtonian fluid, my viscosity is a function of the velocity gradient. Okay, this is a non-Newtonian fluid. So what does it mean? It means that as you apply a shear stress and you start generating a velocity gradient, my viscosity changes. And so the response of the fluid changes in time because my viscosity is changing as the fluid is deforming. So as the velocity gradient increases or decreases, my viscosity changes. Okay? Those are non-Newtonian fluids. Examples of non-Newtonian fluids: so the viscosity depends on the shear rate. This is a no viscosity, no Newtonian. Okay. Examples: paint, blood, lava, cornstarch. Okay. There are two types of non-Newtonian fluids. One is called shear thinning, and the second one is called shear thickening. Okay. So shear thinning or pseudoplastic are, for example, paints and ketchup. So if you ever painted your walls, okay, you take the paint from a bucket. Okay, you take some paint with your paintbrush, and it's very sticky. So high viscosity. As soon as you start using your paint, you will see that the stronger you apply the paint, so the more shear stress you provide to the paint, the easier it is to paint the wall. Okay? So the more shear stress with the brush, the easier it is to spread the paint on the wall. And that's because the paint is a non-Newtonian fluid that is shear thinning. So the larger the shear stress, the larger the velocity gradient that you provide to the paint, and viscosity is actually decreasing. It's a shear thinning. So the more velocity gradient, the less viscosity, the easier it is to paint the wall. So paint is a non-Newtonian fluid that is shear thinning. And it's called pseudoplastic, which is this line over here. So this is the shear rate, du by dz, and this is the shear stress, okay, my tau. So and this is a pseudoplastic, this one, okay. And the opposite is a shear thickening. So shear thickening means that the more shear stress you apply to the fluid, the larger the viscosity becomes. So instead of becoming less viscous, it's becoming more viscous with more shear stress. So the more shear stress that you apply, the more viscous it becomes, and the less velocity gradient that you generate. Okay? And an example of a shear thickening is cornstarch. Now we'll see if I manage to show you this funny movie to finish off. Okay, so shear thickening is a non-Newtonian fluid. The more shear stress that you apply, the more viscous it becomes. And sometimes it can assume the properties of a fluid, of a solid. It becomes so viscous that it becomes close to a solid. Okay? And this is an example. So this, let's go back. Okay, this is a bathtub full of cornstarch. Okay? Cornstarch, as you see from that little girl, is a fluid, is a non-Newtonian fluid. Okay? Is a fluid. You see that the fluid is dripping from the girl's hands. Okay? And that bathtub is filled with cornstarch. Now, the more shear stress that you apply to cornstarch, the more viscous it becomes until becoming close to a solid. This is a nice demonstration of shear thickening non-Newtonian fluids. Okay, we'll see a nice example. You see that the girls are putting their hands into the cornstarch. It's a fluid. And now this PhD student will walk on cornstarch. Okay? The more shear stress that you apply, the viscous it becomes until becoming close to a solid. If you stop applying shear stress, see that guy is jumping on a fluid because it's shear thickening. The stronger the shear stress, the more viscous it gets until becoming close to a solid.
Is that only shear stress? Is that only shear stress when it pushes?
You see, and sorry, if they stop applying forces on the fluid, it goes back to its normal rigidity, and which is a fluid, and so you stop walking on cornstarch. But as long as you apply a force to the fluid, so as long as you apply a shear stress, viscosity is increasing because it's a shear thickening, and it has to be a strong enough force acting on that fluid to make the viscosity grow as much as becoming close to a solid. Okay? And as soon as you stop applying the force, the fluid goes back to its normal viscosity and it's fluid. Okay, so that's just...
I have one question.
Yes.
I don't know, what is the density of that fluid compared to what?
What is the?
Density of that fluid compared to what? Ocean water.
What is the density of cornstarch?
Yes, compared to ocean water.
Oh, I don't know, but it must be very dense. I mean, it's very thick already, cornstarch.
That means the density may not also stay constant. I don't know. Would the density also
No, it's just viscosity. It's just the viscosity. So as long as you apply a shear stress, you apply a strong shear stress, viscosity is a function of the velocity gradient. So the stronger the velocity gradient, the stronger the viscosity. And in this particular thickening or dilatant fluid, okay, the viscosity, you see that the slope is going up. In this case, the slope is going up, and so the slope is the viscosity. So the viscosity is growing, so it becomes so viscous that it gets close to a solid. Okay? The opposite is paint, for example. The opposite is paint. The slope is going down. So the more shear stress that you apply to paint, the less viscous, and the easier it is to paint. Okay? So those are two funny examples of non-Newtonian fluids. But we're not going to study non-Newtonian fluids.
Is this thing related to liquefaction? Sometimes some sediments with some content of water, when they are shaken, they become fluid and they start to flow. Some sediments, the liquefaction in liquids, for example, there are sediments with some quantity of water, So whenever they are not shaken, they act as a solid. They can support certain load, but whenever they are shaken, they start to flow.
Okay,
So-
I didn't know.
In Japan,
Yeah, it happens. It's called
In Japan.
liquefaction. Liquefaction.
What in Japan?
when there are earthquakes, there's water that comes up from the ground that it liquefates.
Oh, okay. So you change the viscosity of
Yeah, it
of the
becomes
fluid in that way,
fluid.
and yeah.
Yeah.
Yeah. So other applications are there are many applications of non-Newtonian fluids in the space industry. So, for example, walls that you want, for example, walls to be very light, and structures that you want them to be not so much solid. Okay, but if there is a strong force acting on the surface, you want the surface to be strong enough. Okay, so you can move the surface of the structure, but when there is a heat or there is a force acting on the structure changes the viscosity and becomes strong. So you can play with the viscosity in that way, or the opposite. You want something to have some rigidity, but you want to resist shear stresses, for example, by deforming. For example, in an earthquake, you don't want it to break, you want it to deform. So with a shear stress, you want to be a shear thinning fluid so that it deforms, but it doesn't break when there's a shear stress. But without the shear stress, it has a rigidity. Okay, another example of shear thin. Yes. Ah, thanks. Well, we're done anyway. An example of shear thinning is lava. Okay. So lava is generally thick when it doesn't move. When it starts to move and there is a velocity gradient and a shear stress applied to the lava, it becomes more fluid, let's say, more easy to flow. And when it stops moving and it cools down as well, it becomes thicker. It becomes thicker and much more difficult to flow. Okay, this is the difference. Yes, so this is the difference between dynamic and kinematic viscosity. Okay, so the dynamic viscosity is that mu, which is the proportionality constant in a Newtonian fluid between the shear stress and the velocity gradient. And the kinematic viscosity, which is usually used in the momentum equations, is mu over density. What is mu, the viscosity for an ideal fluid?
0.
0. Thank you. Passed. Any questions?
Okay.
Yes.
Go on. Does it only have to be concerning the non-Newtonian fluids? Does it only have to be a shear stress?
Well, the Newtonian law of viscosity relates the shear stress to the velocity gradient through a viscosity. In a Newtonian fluid, viscosity is a constant. In a non-Newtonian fluid, viscosity changes depending on the conditions.
Okay.
So, depending on the shear stress, viscosity changes because it's a function of the velocity gradient. So, if there is a velocity gradient, viscosity changes. And if viscosity changes, then the fluid properties change with the shear stress.
But the video they were stepping on it like. See, so maybe I was thinking maybe it was a normal stress. I don't know.
It's like normal. They were applying the normal stress.
No,
So it's not shear.
The surface deforms,
Because,
you get a stress issue.
Okay.
So I think.
Okay.
Good. See you in 2 days' time.
Looking up comparing the equations.
Yeah, that's the Yeah, the radius is infinite. The radius is infinite. So, yeah, we have a plane parallel. The length is infinite.
So that one, I think we can use the 6.11.
Factor.
reference of that for no, it's easy.
We try to calculate. Yeah,
Python formula that connects to that one equation.
when we
Maybe
try
that's